Hello, everybody. Welcome to the Monday's lecture. This week and most of next week, probably all of next week, we're going to be talking about a concept called pipelining, which is a way of speeding up the operations of the data path that we have designed so far. So let's go back to that data path, see what's going on with it, and then see if we can improve the speed of operations. Now, this data path, if you remember, basically consists of a bunch of registers or flip-flops. If you remember, we implement the registers as flip-flops, sequential logic. And then around this sequential logic is a bunch of combinational logic that read data from the flip-flops or sequential logic, perform some operations on them, and go to the memory and access the memory if need be, and finally write the results back into the registers. Or on this part up here, they're going to update, this combinational logic is going to update the program counter based on the type of instruction and so on. And we have talked about the circumstances under which program counter gets updated and so on. So the issue with this data path implementation is that all of the operations from the beginning where we read an instruction from the memory, from the location pointed to by PC, to the time that we write the result back into the registers, all of these operations in this combinational and sequential logic here, all of these have to be carried out in one clock cycle. Beginning from here, from the time that we read an instruction from the memory to the time that we write the result back in the registers, all of that would be one clock cycle. So the implication of this design also is that after we finish one instruction in one cycle, then we can go to the next cycle and then execute the next instruction. And when that next instruction is finished, then we go to the following cycle and begin execution of the third instruction. So we are executing one instruction per cycle. And operations like this, while they're okay, they are slow because we are doing one thing at a time. So the idea is, can we speed up the operations by possibly executing more than one instruction during the same clock cycle? And the answer is yes, we can do that through a concept called pipelining. So for the rest of this lecture and the rest of the week and next week, the discussions are going to be on motivating pipelining, basically saying what pipelining is, how it works, and how it can improve operations. Talk a little bit about pipeline performance, how it can improve the speed of operations. Unfortunately, nothing is free. While pipelining allows us to speed things up and perform better, it also has some hazards. There are structural hazards, data hazards, and control hazards. So we're going to spend quite a bit of time on what these hazards and problems are and what are the solutions to them in order to make the pipeline as fast as possible. And then finally, we talk about the particular MIPS data path for different instructions, and then the control for managing the pipeline operations. So let's begin with motivating pipelining, and let's think about doing a task like doing a load of laundry. So for doing a load of laundry, we assume that there are four operations we want to do. We want to wash the load. After it's washed, we want to dry it. After it's dried, we want to fold the clothing, and then we want to put them away in storage. And we assume that each stage of these operations is going to take 30 minutes. So for completing one load of laundry, from the beginning to the time it's put in storage, it takes 2 hours or 4 half-hour operations. So in the case of the non-pipelined operations, and this is similar to non-pipeline MIPS data path. We do one instruction at a time, or in this case, we do one load at a time. So we start the first load here, we finish it after 2 hours. Then we begin the second load by putting it in the washer and then going through the drying and folding and then putting away. And then we start the third one and so on. So in this non-pipelined operation, if I start at 6 p.m., then I'm going to finish at 2 a.m. for 4 loads of laundry. Now, if we pay closer attention, we realize that really washing a load of laundry has nothing to do with drying it. So why can't I do both, both of these operations at the same time? Meaning that as the first load is put into the dryer, then I can begin washing another load, washing the second load, and so on. So that will lead us to a pipelined operations where during the first half hour, we are going to start with washing the first load. And then as the first load moves into the dryer and begins drying, then I can start the second load in the washer. And then the first load gets into the folding station while the second load is being dried and the third load is put in the washer. And then the operations continue. Then put away the first load, fold the second load, dry the third load, and begin washing the fourth load. So with this operations now, I'm able to, at the steady state, I'm able to perform 4 operations at the same time. And one of the reasons that I can do these 4 operations at the same time is because these are 4 independent resources. In other words, one does not depend on another one. And therefore, while, for example, I'm washing the fourth load, I can dry the third load and I can fold the second load and I can put away the first load. So because of this existence of separate resources and independent resources, I'm able to do these operations in parallel. Now, the question is, how much improvement do we get by doing a pipelined operation versus a non-pipelined operation? Well, if we just look at the time that it takes to do these operations, for non-pipeline, it took us 8 hours, in other words, 4 sequential operations, and these each taking 2 hours to complete. It took me 8 hours to finish 4 loads of laundry, while in the pipeline operations, it takes me 3.5 hours. If I start at 6 o'clock, then at 9:30 I can finish the last load. Therefore, my speed up in this case is 8 over 3.5, which is 2.3. In other words, I can do my laundry 2.3 times faster in a pipeline fashion compared to a non-pipeline fashion. So obviously this parallelism is giving us some speed improvement, some speed up improvement. But what's interesting about pipelines is what is called the steady state or the full pipeline. And sometimes it's called non-stop speed up. So a pipeline becomes full when all the stages of the pipeline are operating at the same time. So looking at these operations at this stage, stage 4, notice that all 4 resources are working at the same time. Okay, so at that point, the pipeline is full. And from that point on, it can complete a task at every cycle, meaning that at this cycle, cycle 4, I can finish the first load, and then immediately at the next cycle, I can finish the next load, and then immediately at the next cycle, I can finish the next one, and the next one, and so on. If I had more loads, then I can do that, right? So at the steady state, we are basically completing one load every half an hour compared to the sequential where it took us 2 hours to do one load. Therefore, our speed up is 2 over 0.5, which is speed up of 4. So in general, At the steady state, the the performance of the pipeline is improved according to the number of stages of the pipeline. So if I have 4 stages, like in this case, then my speed up would be 4. If I had 5, then my speed up would be 5 stages, then my speed up would be 5, and so on. In general, when we talk about speed up operations of a pipeline, we are talking about the speed up gained at the saturation point. The reason is that for these 4 loads, notice that once we get one load out every half hour, that's great, but we have also paid an hour and a half overhead to get to the saturation point, to get to this point. So the total time that I calculate is not only the time that these complete, but also I have to add that overhead of filling up the pipeline. Now, if I had, let's say, 1,000 loads of laundry to do, then these initial pipeline doesn't make any difference because it's so small compared to finishing 1,000 loads of laundry much faster. So because of that, then the speed up of a pipeline is typically measured according to its saturation point or when the pipeline is filled up. Now in this case, it makes a difference because our number of tasks are so small, only 4. So while here we get a speed up of 4 at the saturation point, overall we only get 2.3 because we are paying this additional overhead for filling up the pipeline. Okay. So now that we kind of got familiar with the concept of pipelining, let's see how we can convert our MIPS architecture, our data path, into a pipelined operation. So we assume that we have 5 stages for our pipeline: instruction fetch from the memory, instruction decode and register read, next set of operations, and then execution, next phase, memory access, next phase, and then finally write back or writing the results into the register as the last phase of the pipeline. So if I map these stages into the architecture that we have looked at, then this is what we get. The first stage up here is when we do instruction fetch. Then we do instruction decode and register access, accessing these registers in the next cycle. Then we do execution or ALU operations in the next cycle over here. And then we do write back in the next cycle. Then we do memory access in the next cycle. And finally, once we have our memory operations, then we do the write back to put things back into the registers, and then we are done. Okay, so these are the 5 stages of the pipeline. And the implication is that for a design like this, then we can have a situation where we can have the first instruction coming here, getting being read from the instruction memory, and as we are getting the registers for the first instruction, then we can read the next instruction. And as the first instruction moves into the 3rd stage, then we can read the operands for the 2nd instruction and get a 3rd one. Okay, so I'm gonna stop here and then continue on the 2nd segment of the video for the Monday lecture.